This is the cab of the largest steam locomotive ever built. From here, two people controlled 1,200,000 pounds of articulated machinery. The engineer commanded 7,000 horsepower through a throttle, a reverser, and a brake stand. The fireman managed a firebox with a grate area of 150 square feet, feeding it 22 tons of coal per hour through a mechanical stoker, because no human could shovel fast enough to keep it alive. Together, they took a locomotive longer than a modern football field over the steepest grades on the Union Pacific Main Line, the Wasatch Mountains, the Wyoming High Desert, the brutal territory the Big Boy was built to conquer. This is what it was like to actually operate the largest steam locomotive in history. The controls, the coordination, the physical reality of running a machine this enormous over a mountain. Two people, 1 million pounds, one mountain at a time. A Big Boy required two operators like every large steam locomotive. The engineer ran the train, the fireman ran the boiler. But the scale of the Big Boy made both jobs more demanding than almost any other locomotive in American service. The fireman was responsible for a boiler that consumed coal and water at rates no other locomotive matched. The engineer was responsible for controlling an articulated locomotive whose front and rear engines could behave differently on grades and curves. And the territory was unforgiving. The Wasatch Grade, the Wyoming Main Line, mountain railroading where a mistake in throttle handling or boiler management could stall a 3,000-ton train on a grade, or worse, lose control of it on a descent. What it was like to drive a Big Boy is the story of two people managing the most powerful steam locomotive ever built, across the most demanding terrain it was designed for, with the full weight of the wartime freight effort riding on, getting it right. The engineers sat on the right side of the cab. The primary controls were the throttle, which regulated steam flow to the engines, and the reverser, which controlled the valve gear cutoff. The throttle on a Big Boy fed steam to 4 cylinders across 2 engines. Opening the throttle had to be done with care. The Big Boy's enormous tractive effort meant that opening the throttle too aggressively on starting could break the train apart, snapping couplers as the slack ran out violently, or spin the driving wheels into a slip. And the Big Boy had a unique slip hazard. With 2 separate engines, the front engine and the rear engine could slip independently. The front engine, articulated and carrying less weight on grades, was more prone to slipping than the rear. An engineer had to manage the throttle to keep both engines gripping the rails, a more complex task than controlling a single-engine locomotive. The reverser controlled the cutoff, when in each piston stroke steam was admitted to the cylinders. On a Big Boy, the reverser was power-operated, because the forces involved in moving the valve gear of such a large locomotive exceeded what a human could manage by hand on a simple lever. Starting a heavy train required full gear, long cutoff, maximum steam admission, maximum tractive effort. As the locomotive accelerated, the engineer wound the reverser back towards shorter cutoff, reducing steam consumption while the trapped steam expanded against the pistons. The skilled engineer found the cutoff that kept the train moving at the required speed without consuming more steam than the firemen could generate. This was the defining skill of the Big Boy engineer. Coordinating throttle and cutoff to apply maximum power without slipping, without breaking the train, and without demanding more steam than the boiler could produce. On the Wasatch Grade, with 3,000 tons behind the locomotive, getting this balance right was the difference between making the grade and stalling on it. The brake stand controlled the train's air brakes and the locomotive's independent brakes. On mountain descents, brake handling became critical. A Big Boy descending a grade with a heavy train had enormous momentum. The engineer had to manage the air brakes carefully to control the descent without overheating the brake equipment or losing control of the train. Descending the Wasatch with a loaded train was, in many ways, more demanding than climbing it. The engineer had to balance the air brakes against the train's momentum, making controlled brake applications and releases to maintain a safe speed without burning out the brake shoes. There was no dynamic brake on a steam locomotive. Every bit of retarding force came from friction, and friction generated heat that could destroy the brake equipment if mismanaged. But the engineer could only command what the fireman could deliver. And on the Big Boy, the firemen managed the largest appetite for coal and water of any locomotive in American history. No human could hand fire a big boy. The firebox was too large and the coal consumption too high. At full power, the big boy burned approximately 22 tons of coal per hour. A fireman with a shovel could move perhaps 3 tons per hour at a sustained pace. The math was impossible. The big boy used a mechanical stoker, a steam-driven auger that carried coal from the tender through a conduit and into the firebox, where steam jets distributed it across the grate. The fireman controlled the stoker rather than wielding a shovel. But controlling the stoker was a skill in its own right. The fireman regulated the rate at which coal fed into the firebox and adjusted the steam jets that distributed the coal across the 150-square-foot grate. Too much coal in one area, and the fire would burn unevenly, creating cold spots and reducing steam generation. Too little coal and the boiler pressure would fall. The fireman had to maintain an even, hot fire across the entire enormous grate. This required constant attention to the firebox through the fire door, continuous adjustment of the stoker feed and the distribution jets, and an understanding of how the fire responded to the locomotive's changing power demands. And the fireman managed the water. The big boy consumed approximately 12,000 gallons of water per hour at full power. The fireman operated the injectors that fed water from the tender into the boiler, balancing water input against consumption to maintain the correct water level. The water level was a life or death matter. If the water level dropped too low, the firebox crown sheet, the top of the firebox, directly exposed to the fire, could be uncovered. An uncovered crown sheet, superheated by the fire with no water to cool it, could fail catastrophically, causing a boiler explosion. The fireman's management of the water level was, quite literally, keeping the locomotive from destroying itself. On a grade, the fireman's job reached its peak intensity. The engineer demanded maximum steam to climb. The boiler consumed coal and water at maximum rates. The fireman had to keep the fire hot, the water level correct, and the steam pressure at the maximum the boiler could sustain. All while the locomotive bounced and swayed up the mountain and the engineer called for more power. Even with the mechanical stoker eliminating the shoveling, the big boy fireman's job was physically and mentally exhausting. The heat from the firebox, the constant monitoring of multiple gauges, the continuous adjustment of stoker, jets, and injectors. The awareness that a lapse in water management could destroy the locomotive and kill the crew. It was among the most demanding firing jobs in American railroading. The engineer and the fireman were not two people doing separate jobs. On a locomotive this large, they were a single system, and the coordination between them determined whether the big boy conquered the mountain or stalled on it. The coordination between engineer and fireman on a big boy was continuous and critical. The engineer knew the territory ahead, the grade approaching, the speed restriction, the curve. The fireman had to prepare the boiler for those demands before they arrived. Approaching the Wasatch Grade, the engineer would signal the fireman to build the fire and the steam pressure in anticipation of the climb. The fireman would have the boiler at maximum pressure and the fire at maximum heat before the locomotive hit the grade, so that when the engineer opened the throttle to full power, the steam was there to deliver it. If the fireman fell behind, if the steam pressure dropped while the engineer demanded maximum power, the locomotive would lose speed on the grade. On a 3,000-ton train on the Wasatch, losing speed could mean stalling. And a stalled big boy on a grade was an operational nightmare, requiring helper locomotives to get the train moving again. A well-coordinated crew kept the locomotive at maximum sustainable output for the entire climb. The engineer managed throttle and cutoff to apply exactly the power the fire could sustain. The fireman kept the boiler producing exactly the steam the engineer demanded. The two worked as a single system, reading the territory, anticipating the demands, and keeping the enormous locomotive moving. The cab environment made the coordination harder. The big boy cab was hot from the firebox, loud from the exhaust and the machinery, and in constant motion as the locomotive worked over uneven mountain track. The crew communicated through hand signals, brief shouts, and the unconscious awareness that experienced partners developed over years of working together. The big boy's appetite for fuel and water meant frequent servicing stops. The crew managed the locomotive's consumption to reach the next coaling and watering facility. knowing that running out of coal or water on the line was a serious operational failure. The firemen tracked the tender's reserves throughout the run. The territory the Big Boy worked was among the most demanding in American railroading. The Wasatch Grade in Utah, the high desert of Wyoming, the mountain crossings where weather, altitude, and grade combined to test the locomotive and the crew. A Big Boy crew earned their position through demonstrated competence on this terrain. The engineers and firemen who ran Big Boys were among the most senior and respected operators on the Union Pacific. The locomotive was the railroad's most powerful and most valuable steam asset. The Union Pacific assigned its best crews to the Big Boys because the locomotive demanded the best. And because the cost of mishandling a million-pound locomotive on a mountain grade was too high to entrust to anyone less. The Big Boy era ended with the steam era. As diesel locomotives took over Union Pacific freight operations in the late 1950s, the Big Boys were gradually retired. The last revenue runs came in 1959. By 1962, the entire class was out of service. The crews who had operated Big Boys transitioned to diesel locomotives. The two-person steam crew, engineer and fireman working as a coordinated system, gave way to diesel operation that required far less from the firemen and far less coordination overall. The skills that defined a Big Boy crew became, within a few years, historical knowledge. For over 50 years, no Big Boy operated. The 8 surviving locomotives sat as static museum displays. The knowledge of how to actually operate one, the throttle and cutoff coordination, the firebox management, the crew coordination on grades, survived only in documentation and in the memories of the aging crews who had done the work. And then, the Union Pacific restored Big Boy 4014. When it returned to operation in 2019, the railroad had to reconstruct the operational knowledge, training a new generation of crews to operate the largest steam locomotive in the world. The modern 4014 crew operates a locomotive converted from coal to oil firing, which simplifies the fireman's job compared to the original coal-fired operation. But the fundamental coordination remains. The engineer manages throttle, cutoff, and brakes. The support crew manages the boiler. The locomotive still demands the careful operation that defined Big Boy crews 8 decades ago. Today, the crews who operate Big Boy 4014 are among the few people alive who know what it is like to drive the largest steam locomotive ever built. They have reconstructed a craft that had been dormant for over half a century. Every excursion 4014 runs is a demonstration of operational knowledge that nearly disappeared entirely. What it was like to drive a Big Boy was the experience of operating the most powerful steam locomotive in history at the absolute peak of steam railroad practice. 2 operators. 1 million pounds of machinery. The most demanding terrain the locomotive was built for. And the coordination between crew members that turned coal and water and steam into the force that moved a wartime nation's freight over the mountains. The Big Boy was the largest steam locomotive ever built. Operating it was among the largest steam operating jobs ever performed. And remarkably, uniquely among the locomotives in this series, it is a job that someone is still doing today. Driving a Big Boy was the experience of operating American railroading's most powerful steam locomotive across its most demanding terrain. The engineer and the fireman, the throttle and the firebox, the continuous coordination that turned the largest steam locomotive ever built into a machine that could conquer a mountain. This is part 1 of our From the Cab series, exploring how the most significant locomotives in American railroad history were actually operated. Companion to our What's Under the Hood series on the engineering inside each locomotive. Both series are linked in the description. Part 2 covers driving the Pennsylvania Railroad GG1, an electric locomotive that one engineer could operate alone, with controls so different from steam that the transition required learning an entirely new way of running a train. Subscribe so you do not miss it. There are more locomotives to examine. There are more cabs to climb into. We will keep telling the story of how the machines were actually operated by the people who worked them.